recording doesn't pick up. Okay, good morning, good afternoon, and good evening, everyone. Welcome to our second P2X Top webinar series, and this is a project sponsored by the Royal Academy of Engineering under the funding scheme called Frontier Champions. And in this scope of this funding, we are trying to share to the community about the different approaches for power to X, meaning that power can be electricity, can be solar energy, can be wind, can be different things, and conversion of those energy into X. X can be batteries, X can be hydrogen, X can be chemicals, X can be carbon dioxide derived fuels. And yeah, today we got a very good great honor to host my long-term collaborator, my friend, Professor Qian Wang from Nagoya University. We met when we were at the University of Cambridge at the Reisner Group, and we were both very excited about the aspect of artificial photosynthesis. Yeah, today, Professor Wang will talk about scalable and efficient artificial photosynthesis. So for the solar to chemical conversion, yeah, without further ado, we will start by the presentation from Professor Wang first, for the first 50 minutes, and then we will have about 10 minutes for Q&A. So if you have any questions, please, you can already type down or you can have your question and then raise your hand during the Q&A. Okay, so yeah, the floor is yours, Professor Wang.
Okay, hello everyone. Thank you very much for the kind introduction. So I'm really happy to be here today and grateful for this opportunity to share our research on scalable and efficient artificial photosynthesis for solar to chemical conversion. So our work is focused on developing new technologies that use sunlight to convert carbon dioxide and water into sustainable fuels like hydrogen and methane and syngas. So this is an approach inspired by the way plants perform photosynthesis. So let me start with a brief introduction of my academic journey. I received my PhD from the University of Tokyo under the supervision of Professor Domen, who is a leading scientist in the field of photocatalytic water spreading. And after completing my degree, I continued working in the same research group as part of the Japanese National Qian project, so which aims to develop solar hydrogen technologies. In 2018, I moved to the University of Cambridge as a Marie Curie Fellow and joined the Professor Reisner's group. As well, I co-worked with Qian. So there, my research shifted towards photocatalytic carbon dioxide reduction using sunlight and turning carbon dioxide into useful chemicals like organic acid. So since 2021, I have been based at Nagoya University in Japan, where I established my own research group focused on solar-driven fuel production using a photocatalysis-based approach. So you may wonder why we are focusing on carbon dioxide and solar fuels. So to understand that, we need to look at how carbon moves in nature. Carbon is always cycling through air, oceans, plants, animals, and the soil. So this is called the carbon cycle. Plants, algae, and some bacteria using sunlight to convert carbon dioxide and water into sugars. So this process, we call it photosynthesis. So these sugars store energy and carbon, and they move through the food chain. When living things like people, animals, and microbes breathe or die, they release carbon dioxide back into the air. So sometimes, instead of breaking down, the remains of dead plants and animals are buried deep underground. So over millions of years, with a lot of heat and pressure, these remains became fossil fuels like coal, oil, and natural gas. So these are like ancient forms of stored solar energy. So we call these things fossil fuels. So today, fossil fuels still provide around 82% of the world's energy. So we use them to make electricity, drive cars, and power factories. But when we burn them, we quickly release a large amount of carbon dioxide into the atmosphere. And this is much faster than nature can absorb it. So right now, fossil fuels give us most of the energy we use, but they are limited resources. They cannot last forever. So as the world's population grows and the economies develop, we are using more and more energies every year. So if we continue using fossil fuels at the current speed, oil might run out by 2052, gas by 2060, and coal by 2090. So this is a serious problem because our modern life depends heavily on energy, from transport and farming to house and industry. So as fossil fuels become harder to find, their price will likely go up. So this can cause problems around the world. For example, after the COVID-19 pandemic and the war in Ukraine, so fuel price increased and many countries struggled to get enough energy. So these problems are especially hard for poor people and countries. So when energy costs go up, prices for food, housing, and building materials also rise. Now, this can make life very difficult for people who already have limited resources. So fossil fuels are not just running out, they are also causing climate change. About 90% of human-caused carbon dioxide emission came from burning coal, oil, and gas. Since the Industrial Revolution in the 18th century, the amount of carbon dioxide in the air has increased by about 50%. So this increase is much faster than any natural change in the last thousands of years. So as carbon dioxide goes up, so does the Earth's temperature. So global temperatures has already increased by about 1.3 degrees Celsius compared to the pre-industrial times. So some years are even hotter. So this extra heat causes problems like stronger storms, floods, melting ice, and damages to ecosystems. So scientists are very confident that more greenhouse gases mean more warming. However, this warming does not happen equally in all places. Some areas, especially in the northern hemisphere, are warming much faster. So in fact, some regions have already gotten more than 5 degrees Celsius warmer. And the study called The Future of Human Niche says that by 2070, places like Thailand could have an average yearly temperature of over 29 degrees Celsius, similar to the hottest part of the Sahara Desert today. So at those temperatures, even a small heat wave can be dangerous to human health. So this kind of extreme heat affects people's ability to walk, grow food, and stay healthy. So well-rich cities may use air conditioning, so many poor people, they cannot afford it. So if nothing changes, some places could become too hot to live in for part of the year. So we face two major problems. First, fossil fuels are limited. Second, using them is heating up our planet. The solution is to move forward energy that is clean, renewable, and does not run out. So this includes solar, wind, water, and geothermal energy. So these resources are available in many parts of the world and do not produce carbon dioxide. But to use them, we need new technologies that are efficient, affordable, and can work on a large scale. So that's what our research is trying to do. We want to store solar energy in chemical fuels like hydrogen and methane by using artificial photosynthetic technologies. So this way, we can create clean fuels from water and carbon dioxide using sunlight. These solar cells can be used in cars, power stations, and factories without adding more carbon dioxide to the air. So to understand why we need better fuel technologies, let's look at a simple example. So powering a car for 300 miles, diesel fuel is very compact. So you only need 33 kilograms of the fuel and a small 33 little tank to go that far. But diesel is a fossil fuel and pollutes the air. Hydrogen is much cleaner. It has a lot of energy per kilogram. So, and you only need 6 kilograms of it. But the storage tank must be very large and heavy. So around 260 liters and 125 kilograms, because hydrogen gas needs high pressure to stay compact. At last, we look at the batteries. Batteries are safe and quiet, and they do not produce emissions while driving, but they are heavy and take up a lot of space. So to drive 300 miles, a battery system might weigh 830 kilograms and take up 670 liters, far more than the diesel or hydrogen. So diesel is still the most efficient in terms of weight and space, but it is not sustainable. Batteries are great for short trips and city driving, but it's not suitable for example, the airplane. Hydrogen has a great potential for long distance and heavy duty use, but we need a better way to make green hydrogen. So let's back to the solar energies. Solar energy is the most attractive renewable replacement for fossil fuels. However, due to the diffuse and intermittent nature of solar irradiation, energy harvested from the sun must be converted into other energy carriers like electricity, like the solar cells do, or the chemical fuels that are storable, transportable, and usable upon demand. So this requirement has motivated the development of sustainable artificial photosynthetic processes with the aim of generating fuels from water and carbon dioxide using the solar energy. So directly converting carbon dioxide and water into high-value chemicals such as hydrogen, carbon monoxide, formic acid, methanol, and methane, while artificial photosynthetic processes represent a viable alternative to help close the global carbon cycle and produce renewable chemicals. So many artificial photosynthetic technologies exist in various stages of development, and this can be broken down into the following 3 main categories: photocatalysis, photoelectrochemistry, and photovoltaic-driven electrolysis. So in the photocatalysis system, nanoparticles of semiconductors are suspended in the electrolyte and conduct both reduction reaction and water oxidation, such as here it shows the reaction for the water splitting reaction to produce hydrogen and oxygen. So sun shines, so the sun shines at the photocatalyst powders dispersed in a pool of water, and then the hydrogen is readily obtained. So the photocatalysis system offers a low process cost and simplicity of design and a large-scale method for photocatalytic reactions. A photoelectrochemistry system is composed of an electrolyte, an N-type semiconductor as anode, photoanode, and a P-type semiconductor as the photocathode, with a semiconductor and liquid junction. So a PEC cell system is composed of these components, and the photo-generated charge carriers are separated, and the minor carriers, for example, holes in the P-type material and the electrons in the N-type material, move within the semiconductor liquid interface. In the PEC systems, reduction and oxidation take place at two different photoelectrodes. And in the photovoltaic electrolysis system, a solar cell is connected to anode and a cathode. In the PEC systems, all these steps are performed within the PEC cell. However, in the PV-driven electrolysis design, the charge carriers are photoproduced and separated in a PV component, while the catalytic conversions and the mass transfer take place in the electrolysis unit. So the scientists in Japan have demonstrated that the water splitting can be achieved in a relatively large scale using a photocatalyst panel based on using the photocatalyst powder. Here is the alumina doped strontium titanate. So we can see that it's white, but it's actually composed of numerous photocatalyst particles. So the panel was prepared by simply drop casting the photocatalyst powder on glass plate. As we can see in this movie, the water splitting panel generates hydrogen and oxygen gases bubbles when exposed to natural sunlight. So more impressively, this 1 square meter panel reactor system was expanded to a 100 square meter solar hydrogen production farm and demonstrated a safe operation for over several months with a maximum solar to hydrogen conversion efficiency, STH, of about 0.76% and then natural sunlight irradiation. So the simplest approach to artificial photosynthesis is to use a single photocatalyst that can drive the full reaction. So for example, for the water splitting, over water splitting reaction, when the photocatalyst is exposed to sunlight, the electrons are excited from the valence band to the conduction band of a semiconductor and generating the electron and the hole pairs. So these excited charge carriers then migrate to the surface of the particles where they drive the redox reactions. So especially the electrons reduce proton to produce hydrogen gas, while the holes oxidize water molecules to produce oxygen. So for this process to occur, the conduction band of the photocatalyst must be more negative than the reduction potential of proton, and its valence band must be more positive than the oxidation potential of water. So in other words, the semiconductor must have a band gap wide enough to cover both redox reactions. So at the same time, since sunlight is strongest in the visible light range, it is important to use the photocatalyst that can absorb visible light efficiently. This is key to achieve high STH efficiency. So it means that we need a semiconductor with narrow band gap to absorb more sunlight. So how to balance this requirement, a wide enough band gap for water splitting and the ability to absorb visible light is very challenging. So as a result, only a few photocatalysts reported so far can carry out overall splitting using visible light. So why is it so difficult to develop a visible light-driven photocatalyst? The overall solar energy conversion efficiency using a semiconductor photocatalyst considers the efficiencies associated with three fundamental processes: the photon absorption to generate electron and hole pairs, separation of the charge carriers, and their migration to the surface. And the last step, the surface reaction involving the charge carriers at the solid liquid interface. So to initiate and drive the electron transfer, some additional kinetic overpotentials are necessary. Otherwise, the carriers will tend to recombine in various ways, such as the bulk recombination and depletion region recombination. So we are facing a challenge that we hope the band gap of the semiconductor is as small as possible to absorb more sunlight and increase the absorption efficiency. But it will cause a decrease in the overpotential and also a low charge separation efficiency. So the question is how to facilitate the charge separation while ensuring a high light absorption ability. So the first strategy we used is the reduction of the band gap to ensure effective light harvesting. So although the overpotential will be reduced with decreasing the band gap of the light absorber, the development of new narrow band gap semiconductor is still necessary because the oxide material are unlikely to achieve an STH of 10%, even if its quantum efficiency achieve 100%. So in contrast, a semiconductor capable of harvesting light up to 650 nanometers, like exemplified by oxysulfide material, can have a quantum efficiency of 50% to achieve the target STH of 10%. So that the requirement for carrier separation can be somehow reduced, because we think that the STH, the target STH for the real practical application is about 5 to 10%. So using an oxide material cannot achieve this objective. As a result of the lower electronegativity of sulfur compared to oxygen, the band gaps can be reduced by introducing the sulfur in oxide material because the hybrid sulfur and oxygen optals forms valence band at positions more negative than those of the valence band resulting from only oxygen optals. So however, the utilization of such materials for overall splitting is still challenging because as we discussed, the low overpotential may cause a low charge separation efficiency, and the oxygen and the oxysulfide material have suffered from the lack of the stability for the water-oxidation reactions, because the sulfur on the surface can be oxidized by the holes rather than the oxidation of water. So to overcome these hurdles, we loaded both the oxygen evolution co-catalyst and hydrogen evolution co-catalyst on the semiconductor to capture the photoexcited carriers for the redox reactions and suppress the photocorrosion. So the co-catalyst functions as active site for the surface reactions and also reduce the reaction activation energies of the reaction. Therefore, both the charge separation and the surface reaction efficiency can be promoted. So we will give an example of the Ethereum titanium oxysulfide. So this material responds to a large portion of the solar spectrum owing to its narrow band gap. However, this material has not been used for overall splitting successfully due to the competitive self-oxidation of sulfur ions. To stabilize the yttrium titanium oxysulfide, we loaded iridium oxide and rhodium on the semiconductor as oxygen and hydrogen evolution co-catalyst respectively. The iridium oxide co-catalyst were loaded on the semiconductor surface by absorption, and the rhodium are deposited by photodeposition. So through this way, the rhodium co-catalyst were coated on different regions to the iridium oxide on yttrium titanium oxysulfide, because the photodeposition method allows selective deposition of rhodium nanoparticles on reduction sites, so that it will not cover the iridium oxide, because the iridium oxide functions as oxidation sites. So therefore, simultaneous production of stoichiometric amount of hydrogen and oxygen from water was achieved on yttrium titanium oxysulfide. We therefore demonstrate photocatalytic overwater splitting using oxysulfide as a photocatalyst without sacrification reagent. And also, this is the first demonstration of using a material with an absorption age of as long as 640 nanometer. So more to the next point, another approach to harvest the sunlight efficiently is to construct a desking system based on the two-step photoexcitation of an hydrogen evolution photocatalyst HEP and an oxygen evolution photocatalyst HEP, both having the narrow band gaps. So we can see that the desking pathways is attractive because the band gap of the photocatalytic material does not have to straddle both the hydrogen and oxygen evolution potentials. For the HEP, it's not necessary to have a valence band more negative than the oxygen evolution potential. And for the OEP, its conduction band can be also below the hydrogen production potential. So the system will be useful if we use the semiconductors, which can use for only hydrogen evolution or oxygen evolution as one side of this system. So the traditional desking systems are normally constructed in a powder suspension way. So where the HEP and the OEP powders are dispersed in an aqueous solution containing redox mediators, for example, ions and iodide iodate. So however, the major challenge in developing high-performing desking water splitting system lies in the low efficiency of electron transfer between the HEP and the OEP. So we need to achieve this process very effectively. The electron in the conduction band of OEP transfer to the valence band of HEP. But it is very challenging. So and we normally use the redox cappers, which can also cause side reactions and lead to limited quantum efficiency and a low STH, typically less than 0.1%. So therefore, the development of redox mediator-free desking system is desirable. In these systems, interparticle electron transfer can be established by adjusting the pH value of the reactant. So through this way, an electrostatic attractive force can be generated. So the pH of the reactant solution must be selected. For example, in the system that use rhodium doped strontium titanate as HEP and bismuth vanadate as the OEP, can achieve overwater splitting only in acidic conditions. Besides, the interparticle transfer through this way is inefficient to achieve a high STH and limited to 0.1%. In pure water, it shows very poor activity for overwater splitting. So to overcome these challenges, we have designed and developed a unique device. We call it photocatalyst sheet. To fabricate the photocatalyst sheet, we utilized a particle transfer method to fix the semiconductor powders on a conductive layer, such as gold or carbon. So therefore, the traditional redox mediator in the solution are replaced with a solid mediator for electron transfer. The photocatalyst sheet with a relatively large area, like 6 by 6 centimeter, can be readily prepared by using this particle transfer method. First, we mixed the HEP and OEP particles in an IPA solution, and then drop casting them on a glass plate. After drying, we deposit a thin gold layer on the surface, and then we attach the gold layer with the particles with another glass plate. Lift off the primary glass plate, and after the ultrasonication to remove the particles on the surface, we can get our samples. The SEM-EDX mapping images shows that both the strontium titanate and the bismuth vanillate particles are directly and firmly anchored onto the gold layer, so that the electron could be transferred through the metal between HEP and OP particles. So as we discussed, the mixture of rhodium-doped strontium titanate and bismuth vanillate in an acidic solution, for example at pH 3.5, hydrogen and oxygen can be produced while water splitting. Importantly, when the semiconductor powder were fixed onto a gold layer, the water splitting rate was enhanced significantly compared to the powder suspension system. The rate enhanced about 6 times. In contrast, the photocatalyst sheet without a gold layer, we just fixed the particles onto a carbon tape, exhibit very low activity. So this result suggested that the hydrogen and oxygen were evolved by two-step photoexcitation over the strontium titanate and bismuth vanillate particles, and the charge transfer happens through the gold layer. We also found that the photocatalytic activity of the sheet for overwater splitting was almost independent of the pH of the aqueous reactant solution. This result is quite distinct from the case of the powder suspension system. So this observation provides further evidence that in the photocatalyst sheet, electron transfer relies on the metal layer rather than the aggregation of the particles. So the photocatalyst sheet achieved a pure water splitting at neutral pH with an STH of more than 1%. So the value is more than 10 times higher than that of the conventional suspension system. We also replaced the gold layer with an earth-abundant and conducting carbon layer for the electron transfer. It shows that an STH of 1% at ambient pressure for overwater splitting. So as we can see in the video, the hydrogen and oxygen bubbles are released from pure water and one-sign irradiation. We do not need to add any redox mediators, sacrification agent, external bias, and adjust the pH of the reactant. Just using pure water, we can obtain hydrogen and sunlight irradiation. So the photocatalyst sheet shows high photocatalytic activity because the electron transfer between the photocatalyst is facilitated due to the effective metal semiconductor junctions, and the charge recombination in the photocatalyst sheet is thus suppressed significantly. The photocatalyst sheet with a large area can also be prepared using screening printing, which is a cost-effective and readily accessible printing technique. So these units, regardless of their size, effectively split pure water without the assistance of electrolyte or buffer agent, and we get the STH of about 0.4%. So because the activity of the sheet system is independent of the pH of the reactant, various photocatalytic materials can be applied to photocatalytic sheet for that skin water splitting, because the choice of the materials is not limited by the size of surface charges at the working pH, because we know that some of the materials, such as the oxynitride or oxysulfide materials, are not stable in acidic conditions. So in our work, various semiconductors, including oxide material, oxynitride material, oxysulfide material, and selenide, have been successfully applied in the photocatalyst sheet for solid hydrogen production while water splitting, and this demonstrated the versatility of the sheet design. So we were thinking if the photocatalyst sheets can be applied to other artificial photosynthetic reactions, for example, carbon dioxide reduction. The semiconductor often show high activity and stability for oxidation reactions, but typically give poor ability and selectivity to carbon dioxide reduction. In contrast, the synthetic molecular catalysts have been extensively developed for achieving carbon dioxide reduction with high selectivity. However, most metal complexes currently used only as a homogeneous catalyst in organic solvents. So hybrid systems that immobilize the molecular catalyst on the surface of inorganic semiconductor particles allow their use in a wide range of solvent, including the aqueous solution. So most importantly, through this way, we combine the high selectivity of the molecular catalyst for carbon dioxide reduction, and also the strong oxidation power of the inorganic semiconductors. So taking the advantages of that skin configuration and the photocatalyst sheet design, we combined a hybrid photocatalyst for carbon dioxide reduction and another semiconductor photocatalyst for water oxidation. So using a cobalt beryllium modified dead skin system consists of strontium titanate and bismuth vanadate, scalable and selective solid-driven carbon dioxide conjugated with water oxidation is achieved. When the sheet device is irradiated with simulated sunlight, the electrons and holes are generated in both strontium titanate and bismuth vanadate. The electrons are transferred from the conduction band of bismuth vanadate to the strontium titanate through the gold layer, and the electrons in strontium titanate reduce carbon dioxide to formate with the aid of the molecular complexes as the carbon dioxide reduction co-catalyst. At the same time, the holes in the bismuth vanadate oxidize water to produce oxygen with the ruthenium oxide co-catalyst. So in the investigation of the photocatalytic performance, we observed simultaneous production of formate and oxygen occurred over the cobalt beryllium loaded sheet and simulated sunlight irradiation. So the hybrid photocatalyst sheet enabled an solar to formate conversion efficiency of about 0.08%. And the selectivity for formate production is close to 97%. So the evolution of oxygen in an stoichiometric ratio demonstrate a clean conversion without the need for sacrification agent. The isotopic labeling experiment also confirmed that the formate result from the carbon dioxide. And then we prepared a sheet with an active irradiated area of about 20 square centimeter. The sheet produced formate with an solid to formate conversion efficiency of about 0.06%, which is comparable to those detected with the smaller samples, the samples with the irradiation area of about 1 square centimeter. So this experiment demonstrates the scalability of our photocatalyst sheet system. So due to the unique structure of the photocatalyst sheet, the pH gradient and IR drop between the reduction and oxidation reaction can be effectively suppressed. So the photocatalyst sheet with high activity is scalable. The photosynthetic reactions over the sheet was carried out for 24 hours, with carbon dioxide purging every 6 hours. So the formate and oxygen formation rate remained at about half of the initial activity after 24 hours. And we found that the cobalt amount also dropped by half after the 24 hours. So we reloaded the cobalt braiding on the sheet, and the activity recovered up to 80%. So this result suggested that the decrease of the activity is mainly attributable to the decrease in the number of the active sites rather than the essential deterioration of the sheet structure. So the sunlight-driven carbon dioxide reduction to form multi-carbon product using inorganic catalyst is very challenging because this typically provide poor selectivity towards multi-carbon product and requires additional electricity input to offset the large overpotential requirement. So in contrast, non-photosynthetic carbon dioxide fixing bacteria have metabolic pathways that can produce multi-carbon product from the carbon dioxide with high selectivity. So hybrid bioabiotic system consisting of synthetic light absorbers assembled with carbon dioxide fixing bacteria provide the opportunity for solar-powered carbon dioxide to multi-carbon conversion, which combines the efficient light harvesting capabilities of semiconductor and the strong catalytic power of a living biocatalyst. So because the photocatalyst sheet achieve overall splitting without adjusting the pH or adding a buffer solution, they are expected to be a promising platform for the assembly of a hybrid bioabiotic systems due to the high hydrogen production efficiency and the operated at a biocompatible neutral pH. And here we choose Spromusa as the micro B because it can effectively catalyze the carbon dioxide to acetate using the hydrogen or electrons directly from an electrode in microbial electrode synthesis. So we prepared and photocatalyst sheet using ITO as the solid state charge mediate to connect the strontium titanate and bismuth vanadate. And such a biohybrid system simultaneously produced acetate and oxygen in the expected 1:2 ratio and one sign irradiation. A small amount of hydrogen also is also detected. So accordingly, the selectivity for acetate formation in the reduction or induction reactions is about 90%. And only for the carbon dioxide reduction, the selectivity is about 100%. A solar to acetate conversion efficiency is close to 0.7%. And then we used a system employing the photocatalyst sheet in a separate chamber from the Spromusa with the headspace connecting the two chambers. This system produced only 16% acetate of that obtained from the integrated system. So the selectivity of acetate in the obtained product from the reduction reaction was only 7%, and the main product is hydrogen. So this result suggests that growing bacteria directly at the hydrogen evolution sites enables the biocatalyst to operate at high local hydrogen concentrations. So it avoids the need for the accumulation of high concentration of bulk hydrogen in the headspace. And then we proposed a working mechanism of this hybrid biotic hybrid system. The hydrogen and oxygen production reaction take place on strontium titanate and bismuth vanadate, respectively, and the sunlight irradiation by splitting water into hydrogen and oxygen. So the produced hydrogen is taken by the sporomusa to perform the carbon dioxide reduction and produce acetate via the Wood-Lindau pathway. Additionally, the sporomusa can also use the photogenerated electrons from the strontium titanate to perform photosynthetic process. So to demonstrate the accumulation of acetate in our hybrid system, we directly use the reaction medium obtained after 15 hours of the reaction as the feedstock for a bioelectrochemical anode of a micro-B fuel cell. The bioelectrochemical system consists of a porous ethyl electrode inoculated with gel bacter. Gel bacter is an electric bacterium that can grow using acetate as the electron donor and uses the electrode as the electron acceptor. So at the potential of 0.1 volt versus SHE, the gel bacter starts to produce current by oxidizing the acetate back into the carbon dioxide with a Fladdick efficiency of about 88% for the acetate oxidation. So this demonstration saves an illustration for a closed carbon cycle in which the solar energy is stored by conversion the carbon dioxide to acetate and released back to the carbon dioxide when we're producing the renewable electricity. And recently, our work demonstrated an alternative way to avoid the side reactions caused by the redox mediator. So in this reaction, when we can construct the dead skin system, we still use the redox cables, not use the solid state mediator. So in this system, we separate the hydrogen and oxygen evolution into two different cells. And so the one cell is for the hydrogen evolution, and in here we use the perovskite photocatalyst to reduce the proton to produce hydrogen. It also oxidizes the aldehyde to form the aldehyde. And in the oxygen evolution cell, the bismuth vanadate oxidizes water to produce oxygen. The bismuth vanadate is also connected to a carbon close electrode, which is inset into the hydrogen evolution cell. And on the carbon close electrode, the aldehyde is reduced back to the aldehyde. Aldehyde is reduced back to the aldehyde. So this system suggested that in the oxygen evolution cell, there is no redox cables. So in that way, we can completely avoid the side reactions on the bismuth vanadate in this solution, in this system. And most importantly, because the hydrogen and oxygen are produced in separated cells, the back reaction of the hydrogen and oxygen to recombine to react to form the water reaction can be completely suppressed. So thanks to this design, we achieved an solar to hydrogen conversion efficiency of about 2.5% with this dead skin system. And then we immobilized the perovskite particles on a substrate and formed the photocatalyst sheet structures. And using this kind of scalable systems, we demonstrated a stoichiometric hydrogen and oxygen produced and collected separated in different chambers, achieving an average STH of 1.21% for solar-driven overall splitting during a week-long test under natural sunlight conditions. So this is a system with the areas of about 700 square centimeter. So I would like to say that we have demonstrated that the sustainable hydrogen and some chemicals from the carbon dioxide can be produced using sunlight as the driving force. We don't need to use the electricity as the energy input. So to achieve this carbon cycle using the solar fuels, we need to develop efficient, scalable, and stable systems for the conversion of carbon dioxide and water and the sunlight radiation, so that we may contribute to the establishment of a sustainable society in the future. So at the last, I would like to thank my supervisor during my PhD study at the University of Tokyo, Professor Dorman, and my host when I worked at the University of Cambridge, Professor Resner, and all my colleagues, our collaborators, and my current group members. I also appreciate the fundings for supporting our research. Thank you very much.